We have already mentioned regarding different types of thermodynamic processes. The main types are isothermal process, adiabatic process, isobaric process, isochoric process, cyclic process, reversible process and irreversible process. So the first one is isothermal process. The term iso means constant. So this is a constant temperature. So a process in which pressure and volume change at a constant temperature is known as an isothermal process. So temperature remains constant and volume and pressure may change, or they must change. And one of the main examples for isothermal process is phase change. This you have already familiar with. That means if you are heating water, say at from normal temperature 30 degrees Celsius, its temperature will increase up to 100 degrees Celsius and it will boil. That's a phase change. And you know this fact that until the complete water is converted from water to water vapor, the temperature remains constant at 100 degrees Celsius. So that's the same case with the freezing of water to ice or melting of ice to water, etc. So during phase change, temperature remains constant. So phase change is a very good, or it is a best example for isothermal process. An isothermal process must be infinitesimally small or infinitely slow so that the system is always in perfect thermal communication with the surroundings. So this is one of the main conditions for isothermal process. It is a slow process. The reason is that your system is at a constant temperature. So if there is a tendency to decrease its temperature, it must absorb heat from surroundings to maintain that temperature level. And if its temperature is slightly try to changing or try to increasing, it must liberate that amount of heat to the surroundings. Then only it can be kept at a constant temperature. And the flow of heat is not a all of sudden one. It takes some time. So that is why you are saying that isothermal process must be infinitesimally small so that the system is always in perfect thermal communication with the surrounding. So that you can say that isothermal process taking place at a constant temperature and it is a slow process. And the equation of state for isothermal process of a perfect gas you can write as PV equal to constant. And this is from your ideal gas equation. For ideal gas equation we have PV equal to nRT, n number of moles, R universal gas constant and T is the temperature. And you can see that n constant and R is constant. And for isothermal process, T is also constant. So nRT is a constant. That is why you can write as PV equal to constant. And this is the next process, adiabatic process. In adiabatic process, the system is isolated from the surroundings so that heat neither enters or leaves the system. So that is the speciality of adiabatic process. And in adiabatic process, pressure, volume and temperature may change. So, we haven't measured any constant conditions here. There is no heat transfer. That means heat energy flowing or into the system or out of the system is zero. And all of these three quantities, pressure, volume and temperature may change. And for perfect thermal isolation, adiabatic process is quick and sudden one. This is an important concept. your system and surroundings should be thermally isolated. So, if a process is taking place, there is a possibility of either heat entering or heat leaving. And actually, you can't be a separation which is 100% insulated. So, the concept is that the process is very quick so that there is no time for heat transfer. Actually, heat transfer is a very slow process. So, if it is taking place very quickly or rapidly, there will not be any heat transfer between system and surroundings. So, adiabatic processes are very quick processes. Like examples, bursting of a cycle tyre. This is a common example for adiabatic process. Bursting of a cycle tyre. And the equation of state for adiabatic process is PV raised to gamma equals constant. This equation is also familiar to you, and we will derive that equation later, and where that letter gamma is ratio of specific heats Cp by C. Now, a process taking place at a constant pressure is called an isobaric process, where that bar represents the term pressure, pressure, that means isobaric. And for isobaric process, the equation of state you can write as, again we have the equation PV equals nRT. For isobaric process, you can have P equals constant. So from that PV equals nRT, nR constants, P is also constant. So nR by P, and here it is V by T. So V by T is equal to constant. Example, boiling water in an open container. So in an open container, always the pressure above water is atmospheric pressure. And now, a process taking place at a constant volume is called isobaric. And similar to your isobaric process, the expression for isobaric process is P by T equal to constant. And the example is your ideal Otto cycle. In heat engines, we will be studying this Otto cycle. And now we will define the term cyclic process, because in heat engines and refrigerators, we are always dealing with the cyclic processes. And you are also familiar with the cyclic process like a Carnot cycle, etc. So here, after performing a series of processes, if the system is finally brought back to its initial stage, the process is called a cyclic process. So after a series of processes, that means your system is at a particular pressure, volume and temperature. And say it is expanding, contracting, something like that. Or it is undergoing isothermal process, isobaric, whatever may be. And after a series of processes, the system is coming back to the same condition. That means it is again reaching that same pressure, volume and temperature. And such a process you are calling as a cyclic process. And examples of cyclic processes in daily life are working of refrigerator, air conditioner and motor vehicles. In motor vehicles, you have heat engines, and heat engines are undergoing some types of cyclic processes. And now, a reversible process is performed in such a way that at the conclusion of the process, both the system and local surroundings may be restored to their initial states without producing any changes in the rest of the universe. So, here also the system is again coming back to its initial stage, as like we have mentioned in your cyclic process. But the difference is that before starting the process, what was the condition of system and surroundings? It is brought back. And in cyclic process, there is no consideration of surroundings. And this is an example. You can see that water can be cooled to ice. Then ice can be melted. That means heating. It can again become water. So at 0 degrees Celsius, water can become ice. Ice can become water. So this is a reversible process. And an irreversible process is a process that cannot return both the system and the surroundings to their initial conditions. And normally, all natural processes are irreversible. And here you can see that you have a hot body. So normally heat is flowing from hot body to cold body, and always from higher to lower. This is a type of irreversible process, because if it should be a reversible process, the same heat should flow from cold body to hot body, but it is not possible. Heat cannot flow naturally from this cold body to hot body. So this is an example for irreversible process. And now we can look for the conditions for reversible process and irreversible process, or condition for reversibility. And for reversible process, it is performed quasi-statically. That is, the system must pass through states of thermodynamic equilibrium. So actually, a reversible process is taking place quasi-statically, means always nearer to thermodynamic equilibrium, and also it is a slow process. The process is not accompanied by any dissipative effects such as friction, viscosity, inelasticity, electric resistance, and magnetic hysteresis. So this friction, viscosity, inelasticity, electric resistance, etc. they are processes during which energy is always dissipated. That means the process is not accompanied by any of these. So for a reversible process, you can just mention that if you are moving an object, this is not actually thermal concept. If you are moving a body on the surface of, or on a particular surface, if you are moving it from one point to other, it is moving. And if that means from point 1 to 2, and if you are leaving that body at 2, then naturally it will be coming back from 2 to 1 without performing any work on that system. For 1 to 2, you are performing work on that, and by performing work itself, it will coming back from 2 to 1. And this is a process you can consider as a reversible one. But if you are moving from 1 to 2, for example, you are moving a duster over the desk. So actually, when moving from one point to other, you have to overcome the frictional force. From then again going back from 2 to 1, again you have to perform work. That means you have to move it in order to overcome the frictional forces. So that frictional force is actually preventing that motion. So that frictional force is a type of dissipative forces. So it is consuming some energy. And now conditions for irreversible process. So where the conditions in reversible process, it should not be satisfied here. That's the simplest one. So the thermodynamic equilibrium is not satisfied For reversible process, it should satisfy. That is, the conditions for mechanical, thermal and chemical equilibria are not satisfied. And the dissipative effects such as friction, velocity, viscosity, inelasticity, electric resistance and magnetic hysteresis are present. Now, thermodynamic processes can be studied by drawing graphs between different thermodynamic coordinates. The graph between pressure and volume, known as PV diagram, and the graph between pressure and temperature, known as PT diagram. This you might have studied in chemistry as your phase diagram, the PT diagram. Also, you have graph between temperature and volume as volume temperature or VT diagram, graph between temperature and entropy as TS diagram. So, we will be discussing about this PV diagram, and there is another name for this PV diagram as indicator diagram. So, here a graph with pressure P on y-axis and volume on x-axis. It's not v-axis, it is x-axis. Sorry. Volume is on x-axis and it is called a PV diagram or indicator diagram. And now we will look for PV diagram for different types of processes. This is the PV diagram for an expansion process. Expansion means volume is increasing. You can see that this is the initial stage and this is the final stage. The direction of process you can see from this arrow mark. So, first initial volume, that means volume is low, finally volume is high. So, it is expanding. So, when volume is increasing, you can see that pressure is decreasing. And this is that of compression, that means initial volume is greater than final volume. So, from final volume you are going to, from an initial volume you are going to a final volume. So, volume decreased and the pressure you can see as increased. And this is for isothermal process. Initially pressure P0, V0 and finally to P1, V1. And this is at a constant temperature that you have just marked it as T is equal to constant. But only P and V are actually marked in this. So, this is a curve like this. And this is adiabatic process. This is again another curve. There you have pressure, volume. Then temperature is also different. P1, V1, T1 to P2, V2, T2. Now, isobaric process. So, isobaric process, pressure remains constant. That means, during the whole process, pressure remains constant. So, it is a line or it is a horizontal line, or you can see that that line is parallel to the volume axis. And during isochoric process, volume remains constant or you are getting a vertical line. That means volume remains constant, only pressure is changing. And this is for cyclic process. So, you have started from this A and a type of compression through this path ADC. And from C, it is going back to A through another path. And this is cyclic process. And this is a reversible process. You are going from A to B. You have this arrow mark from A to B and from B to A. After series of process, system is coming back to the initial conditions. Now you compare these two, cyclic process and reversible process. In cyclic, initial point is A and after series of process it is again at A. A to B and from B to A. Here also A to B and B to A. So in cyclic process, the two paths are not actually same. They are different. But only the initial and final conditions are same. But in reversible process, the system is coming back to the initial conditions through the same path. So that is the speciality of reversible process. And this is cyclic process. In cyclic process, the paths are not same. And if the paths are same, it is reversible. And in the same graph, we have marked this isobaric process, isothermal process, adiabatic process and isobaric process. We have mentioned that isobaric process is a horizontal line, that means pressure constant, isobaric, volume constant, a vertical line, and these are isothermal and adiabatic processes. And this isothermal and adiabatic are actually curves. But you can distinguish between isothermal and adiabatic as there is a difference between their slopes. That we can mention only after introducing the concept of work that we will do in the next chapter.